page. Okay, so we were talking about the 1D hydrogen chain, and we were looking at, as we increase the number of hydrogen atoms, we were going from 1 all the way to infinite, and we were having them loop upon themselves. So they were making sort of ring-like structures. We had number of hydrogens, we had the geometry, and then we had an energy diagram. And what number of hydrogens did we do? We did 1, 6, and then we jumped to infinity. We drew the geometry of each of them, where these were just the atom nuclei centers. And then here I got lazy and just went whoop, and that they're connected all the way in between. We drew the electronic structure for some of these things. This one was just a 1s. Did we draw electrons yet or no?
We started filling and then you said, actually, I don't want to fill that.
Okay. Yeah, I don't want to fill them yet. Okay. When we moved from 1 to 2 H's, what happens? How many MOs do we get? 2. And what do we label them? Sigma star, sigma. I'm going to draw it in yellow. We would represent it. Whoa, wrong. Overlap, positive overlap. And this one, how would that one change? Yep, destructive. We're not showing them mixing. We're just showing the AO signs. Then we went to 3, and we ended up with a degenerate state like this. If we were to draw out the bonding combination, it would look like that. What about these other two here? Yep, like that. Looks like a bird to me, the messed up eye. 4, how did we draw that one? Yeah. Like that. I think we drew the MOs for this one, right? I'm invading the space of the other one. Okay, how would do I need to bother with the bonding one? Do I have to fill it at all, or is it good? What about these next ones? Yep, 2 on the same side. Then how do you want to fill that one? Yeah. Okay, then the worst case scenario, the completely anti-bonding case, which one do you want to shade in? Which? Okay, we'll do it that way. Yeah. Okay, now we move to 5. How's that one going to look? Yep. The kind of cool thing is with Huckel theory, if you draw these with the pyramid down, or the point down, it gives you the energetic ranking. Like if this guy, if I turned it a little bit, we have a diamond there. So this one's going to look like this. It gets a little lower in energy. I should have drawn that a bit better. And that's benzene. You've seen that in Orgo, I bet.
No, I'm never.
Orgo, oh, it is Orgo too? Okay. Oh no, I meant the Huckel orbitals. When I took...
I thought you were just saying I've never seen benzene before.
Oh, no, yeah.
I was like, no, I've never.
Yeah, guy works in a refinery, has never seen benzene. I doubt that, but... Like I knew mechanics that used to wash their hands and the stuff. Yeah, it's the most delicious. Oh yeah, Italian. I love the smell of Italian. I used to be the kid that I would beg my parent if I knew they were going to a gas station, I was going with them because I could smell the gas. Gas sniffer too. Yep. I don't smell it anymore. I don't know if COVID killed it for me or I've just destroyed my nose with too much organics. I know Dr. Ogawa can't smell stuff either, so maybe it's just something. What's that? He can smell stuff still. Yep. P. Schneid smells things way too far away. All right, I didn't give myself enough space, so I had to move it over for 6. What's that one going to look like? Yeah, hexagon, these are the points. Then there's another one up here. Do we want to draw the MOs or do you feel okay? Might benefit us. That one, I know, I'm sorry. You don't have to draw these things in. I just want to. Yeah. And I like it. Oh, actually, I left him off. Let's leave him off. Can't do it. No. There's one like that. There's also another one where you'd have a node through another way. These ones are missing stuff. That one's completely anti-bonding. All right, let's go all the way to infinite. I'm spending too much time on this molecular stuff. We're done with that. If I had an infinitely long hydrogen chain, how many energy levels would I need? An infinite number. I'm going to draw it this way. And give myself mesothelioma from all the chalk dust that's coming off. I know. It's okay. We can always buy more. For now, until it goes out. Did you see? Yeah. Again, so this type of chalk was going to go away, and then all the mathematicians in the world started hoarding the chalk. You'd have to buy the chalk for like $50 a thing. There was one professor who calculated how much chalk he would need until he died, and he bought all the chalk. That's all of his chalk.
Why was it going to go away?
The company was closing down in Japan.
I'm in South Korea.
Yep, because they knew it's the best chalk. Yeah. Calculated it. So this is not fun to do. If we were trying to draw out systems, we don't want to do that over and over. This is a band. We often draw it this way. This is a simplistic idea, a more molecular orbital way to draw it. But really, we get a band. Now, what is a band? Yeah, rocking out. Guar just came to Albany, so what is an electronic band? They play, metals. At H infinity, we get so many states. They're all slapped together. We essentially have a continuum. So many states. We call this continuum a band. Oh, better. We've dealt with infinitely large periodic systems. What's the benefit of having a periodic system?
Unit cells.
Unit cells. We have translational symmetry. Let's utilize that translational symmetry to talk about the infinite. But since we have an infinitely long we have a crystal, one-dimensional crystal. Crystals have what type of symmetry? Yep. Let's use its translational symmetry. Okay. The next section's titled Baby's First Band Structure.
Oh my gosh, wait, I don't know.
Yeah.
Are we finally following?
Nope.
Have we
We're drooling, but we have a parent that's like mopping it up on her face. Okay. So we're going to draw a crystal, a one-dimensional crystal. What's a one-dimensional crystal? A dot, a line of dots. We're drawing a line. Okay. Trying this out. We can index our H atoms. With n is equal to 0, 1, 2, and so on. And each atom is a point. With a basis function. Which we're going to give the symbol chi sub n. Spaced a distance, a lattice vector, A, apart. What's the basis function we're going to use for a 1D hydrogen chain? 1 what? Okay, I just didn't hear the S part. Yeah, it's a 1S, sorry. Okay. So let's draw this out. Here is each of my atoms in space. We're going to have the value of n. We're going to call the first one 0. Why is 0? Programming reasons. 2, 3. And this thing continues forever that way, and it actually continues forever this way. Okay, now this distance, or unit cell, what length did we say that would be? A. I'm going to call it A. And there's a basis function on each one of these points. We call that basis function chi is 0. What would it be for the second one that we've labeled 1? Yep. Yep, and I'll just keep going. Now, this is an electronic system. We're dealing with electrons here. If we wanted to model this system, what do we need from quantum mechanics? I'm not going to use LCAO here because it's only one, technically only one atom is in our unit cell. What do we need to get the energy of the system? We need a wave function. We can represent. Infinitely long. Represent this chains. I'm going to give you a mathematical proof to do this at some point. So I have k, this is a lowercase k. We're not going to talk about what k is quite yet, but we will use different values of k. Is equal to the summation n e to the I k n a chi n. Okay, so question. What is K? It has to deal with reciprocal space. But what it's really keeping track of is symmetry. It's an index for symmetry. Lily, when you were determining symmetry in inorganic, what did you have to find? You had to find point groups, which led to irreducible representations, right? Or did you talk about? Okay. Has anybody done group theory yet or talked about group theory in any of your math courses? No? Yeah. Did you talk about irreducible representations? Maybe. Okay. Index for irreducible representations, technically. That's how the physicists and the mathematicians would refer to it. When I see it, I think symmetry. So now we're going to ask a series of questions, and you guys are going to find that you have way more intuition about this than you thought. Next question. What does the wave function look like at k hat is equal to 0? Let's look at this in a mathematical sense, and then we'll translate it into a molecular orbital picture. So psi is 0. It's equal to summation of n. We're going to use e to the I, k, n, a, this thing. What's k equal to again? 0. So what happens here? Yep. Comes e to the 0, which is 1, times chi sub n, which really, if we wanted to simplify this, chi sub n. What if I wanted to expand that? What would that look like? And so on. Now think back to linear combination of atomic orbitals, or whenever we were considering wave functions, and we would have sign changes between the wave functions. So I'm going to draw my 1D hydrogen chain s orbitals. There's an s orbital. Okay. I'm going to draw the atom center. That guy. That guy. Okay. These are the basis functions. Does the sign change between them? No. So they should all be the same sign. I don't have any nodes that I have to introduce in here and change the sign. What type of overlap is this? It's constructive, so it's bonding. Since it's all s orbitals, what's the only overlap s orbitals have? This is a sigma bonding crystal orbital, it's called. Okay, I'm going to pick another value of k that's going to seem completely arbitrary, and we'll figure out why soon, that it's important. Next question. What about at k is equal to pi over a? I just erased our summation. It was E, I, K, N, A, right? What's our K value in this case? Yep, pi over A. And then what else do I need up here? N, A. How? What's that? That's meant to be an A. Oh, yep, we're summing over N. I don't know why I wrote an I. My bad, thank you, good catch. Stuck in Gen Chem world. That's why you don't use I as an index. Okay, what's gonna happen here? Yep, A's go away. Oh. Okay. Now we get oh, that's a good catch. There's another way to express this. Anybody know what it is? Oh, it is sine and cosines hidden in there, but there's another way to simplify it. Okay. You can find it in a table. Negative 1 to the power of n chi sub n.
Yeah,
Okay. There's a derivation around somewhere.
It's fine, dude. I can accept it.
I don't. Okay. This is true. Rolled Hoffman, honestly, but I took a lot of mathematical physics too, where I just could see this because this comes up a lot. I dealt with it a lot. Okay, so now let's plot this thing. So if I want to expand this out, first term, n is equal to 0, what's it become? Yep, 1 chi is 0. Then I got n is equal to 1. What's this become? What's the next one? Uh-huh. Man, got the dropsies today. Don't let me hold my kids. Okay. Okay. Now, these are the basis functions, but I have to start coloring some stuff in because we got sign changes. Between the first and the second carbon, what should I do here? Yep. What about for the next one? This one. What type of orbital is this? Yep. Okay, what we're going to do next time is we're going to plot it. Then we're going to start asking questions of ourselves, like, why did I pick that value? What happens when we switch from simple s orbitals to p orbitals and d orbitals? How do these things all change? If I'm doing this, where the hell are the electrons? All of these things are what we're going to talk about, and what you're going to see is you have more understanding of these systems than you think you do. Okay?